Okay, so coming back to the linear functions and the parameterization of linear functions is probably kind of like a step back, but I thought I might show you these ones anyway. So first up, we've got find a Cartesian equation of the straight line defined by the parametric equations x is equal to 3t and y is equal to 2t minus 3. And then we're asked to sketch the graph of the linear function x is equal to 2p plus 4 and y is equal to p minus 2. So let's start off with part A. And what we're going to do is we're going to solve simultaneously equations to eliminate the parameter. Okay, so we've got x. Oh, I'm pretty sure I just changed that, but that's fine. So we've got x is equal to 3t, and we get y is equal to 2t minus 3. What we're going to do is we're going to rearrange part 1, or x, for t. So we can go, so x is equal to 3t, so t must be equal to x on 3. Okay, so just a little bit of manipulation there. What we're going to do then is we're going to substitute that into the equation above, the y is equal to 2t minus 3. So y is equal to 2t minus 3. I'm going to write next to it sub in t is equal to x on 3. So putting it in, we're going to get y is equal to 2 lots of x over 3 minus 3. And so y is equal to 2x on 3 minus 3. And that becomes our Cartesian equation. Nice and simple. Now, what we're going to do... Oh, sorry, that's our value for... Yeah, that is our Cartesian equation. So we just substitute it straight in and we get a value back out. Okay, let's scroll down a bit and continue with part B. So part B says, okay, sketch the graph of the linear function x is equal to 2p plus 4 and y is equal to p minus 2. So again, what we're going to do is we're going to turn this into a Cartesian equation and then we're going to just plot it because we know how to do lines. Lines are quite easy. So x is equal to 2p plus 4. Okay, and what we're going to do is rearrange for p. Now remember, the parametric equations don't have to always be t or p. They can be whatever letter they want to be. We typically don't use x or y though because those are our coordinate values. So rearrange for p. So we're going to get x minus 4 is equal to 2p. And so then p is equal to x on 2 minus 2. Okay, once we have got that, what we're going to do is we are going to substitute p, so sub p is equal to x over 2 minus 2 into y is equal to, and our equation for that one is p minus 2. Okay, so we're going to substitute it into that. So y is equal to, okay, so our value for p, so it's x on 2 minus 2, and then we're going to subtract 2 from that. So my Cartesian equation becomes y is equal to x on 2 minus 4. Now we're not quite done. What we're going to do now is we're going to draw a picture of this equation. Okay, so let's start off by drawing up our Cartesian plane like this. Okay, now we should be able to pick straight away what our y-intercept is, and that's just the value that's by itself. So minus 4 is our y-intercept. Okay, and our gradient is a half. So for every 2 I go across, I'm going to go 1 up. So what I'll eventually hit is I'll eventually hit the 8 because it is a positive gradient. Putting those together, we get something along the lines of that. And here is our sketch for y is equal to x on 2 minus 4, which tells us that all our values for p, so p is equal to 1, p is equal to 2, p is equal to 3, all fit on that line as well. Okay, so back from our parametrics, any point that I pick would also make our parametric equations true as well. Okay, we're also going to have a look at example number 2, okay, before we get to further ahead. So with example 2, what we're going to do is going to convert each linear function to parametric form using the given equation for x. Okay, so this time we've been given a value for x, and all we're going to do is we're just going to turn it into a parametric equation. So this is going like in reverse. So let's start off with, I might just zoom in a bit. Won't let me. Yes, it should. I'm going to zoom in. There we go. And get my pen up. So convert each linear function. Okay, so let's start with part A. So part A says 3x plus 1 is equal to and then x is equal to p. Okay, so if x is equal to p, okay, sub into y is equal to 3x plus 1. And what you'll find is that our equation will just become our parametric form, because this is a nice easy one. So y is equal to, okay, 3p plus 1. So y is equal to 3p plus 1 is the parametric form. Okay, it's that easy. Okay, and that one's quite easy because our value for x is just p. So we're effectively just saying, well, x is exactly p. It's pretty much the same equation, except we just with a different letter, okay, because of that nice, easy substitution. Part B, however, is a little bit trickier because we've got x is equal to 4t. Not that much trickier, but a little trickier nonetheless. So we've got this equation. We get 5x minus 2y. Well, that wasn't me, but okay. And while we're at it, we might move down a bit. Okay, so we get 5x minus 2y, and that is plus 1 is equal to 0, and x is equal to 4t. Okay, so again, we're going to use the given parametric equation, x is equal to 4t, and we're going to substitute. Okay, we're going to substitute, excuse me, into the Cartesian equation. So we're going to substitute x is equal to 4t into 5x minus 2y plus 1 is equal to 0. Now, the nice thing about this is that they already give us x is equal to. We don't have to do any rearranging for this one. So substituting it straight in, we get 5 lots of 4t minus 2y plus 1 is equal to 0. So expanding this out, we get 20t minus 2y plus 1 is equal to 0. Just like that. Okay. And what we can do as well is we can rearrange this for y to get it into gradient intercept form. So we're going to get 20t plus 1 is equal to 2y. And we're going to make y the subject by itself, which gives us sorry, not 20. It's going to give us 10t plus a half is equal to y, or y is equal to 10t plus a half. So we can draw that nice and easily if we want to. Okay, so just on the side, I'm just going to add, therefore, the equations in our parametric form are x is equal to 4t and y is equal to 10t plus a half. Okay, so there's our equations there. Okay, and that makes it a nice and easy one to do as well. Okay, so with that being said, that is the end of the linear part. The next bit and the last bit will be talking about circles. Circles are much trickier than the other two because it relies on a little bit of trig to get what the value for our, or to get what our parametric equations turn into.